think it was before, but it's a lot more straightforward because I only have basically what's working in there. I don't have a lot of different, like how the old code was. So it should be good.
So it is good. Yeah.
It works. I ran it, it works. So the thing is, the problems that I have, I wrote a couple of them down. When I increment data, so I have it run from 0 to 2 pi. If it's at pi over 4, it gives me one answer. But then if I change the increment, which I think is a normalization issue, right?
Yeah.
So if I change it to pi over 8 and have more segments, it increases significantly the total cross section. So I think that if the problem is like, I don't know if I could somehow normalize it to where it wouldn't do that. But that would be one thing.
We are going to meet today, right?
Yes, yeah.
So let's think about it.
Yeah. Then, so I had another idea, unrelated, but in quantum mechanics with Dr. Masvidal, we were talking about Feynman's lectures, how he goes through like the gun argument and then the wave argument. The electrons. I was thinking, why hasn't somebody set up a real gun experiment? Because have you ever heard of airsoft bullets? Airsoft is kind of like paintball, but they're like plastic BBs.
Same right now, yeah.
So why couldn't you set that up on like a tripod stand and then you would take an average of like the velocity, how fast they shoot, so then you can calculate the momentum, you can calculate the Rotary wavelength of the traveling aerosol pellet, and then base your slits on that wavelength. And then you should see, I'm not convinced, why I'm thinking of this, I'm not convinced that if you shot a bullet through 2 slits, you would get a continuous distribution.
You will not?
I don't think so, because you're basing that, how's it going to hit anywhere? It's going to have to deflect off of the surface, off of the 2 walls of the slit. There's only.
But you're suggesting that this will show interference?
I would want to set it up because I'm not convinced that.
Yeah, sure. So here is the closest thing to what you're saying. Yeah, I mean, pellet balls, we said, right? That's relatively very big, right? What they have done is that they can do C-shim atoms. Or even lucky balls, like lucky balls are about maybe 10 nanometers, 1 to 10 nanometers.
Carbon?
Yeah, C60, whatever. Carbon is Buckminster.
Yeah, that's what the dome is.
Yeah, it's based on, so it's called Buckminster. Lucky balls is Buckminster. Polarity. Right. So they take that big molecules and they send it through. But even that was very hot, and they could get this confirmed. But as the size gets bigger and bigger, the claim is that this quantum effect should go away. But you're saying that
I don't know if there would be quantum effects necessarily. I mean, set it up, leave it in a dark room. You know the momentum to a certain extent, but you know there'll be error in the gun anyways. So you shouldn't, like, if you don't measure the pellet anywhere along the flight, then you never know. Like, you want to violate that certain principle, basically.
let's talk. It's important. Let's talk about it. I'm not completely convinced about that. That should show. I mean, if I had to just say yes or no, I would say no. That should not show. But then you seem to have some argument that it's.
I just don't 100% buy the argument of the probability curve itself. Even if it's not an interference pattern, I think there would only be a certain amount of places that the bullet can deflect to. You know what I mean?
Oh, yeah. But then you will get 2 peaks usually. Yeah, but that's all they are saying, right? So is that okay? So this is a. So with this bullets, because of this tiny range. But
Yeah,
that's
I don't
okay.
think. But so that's if you have each one of them closed individually, and then if you open both of them, then it changes to some, a smooth curve across, right? Because you add the 2.
Yeah, if you add these 2, if it is classical mechanics, you get 2. That's it. But Now, if it is quantum mechanics, you get a whole interference effect. Like this becomes a wave. Right? Isn't that? So it becomes like
So I
optics,
think-
you start getting diffraction. Unless you're talking about stone galactic. Stone galactic again is slightly different.
Yeah.
Like if there were spin particles coming in.
Yeah,
Let's
we
talk
can
about
talk
it. I think
about
others might be completely lost.
Yeah.
All right. Yeah, let's talk about it. Okay. Is there anyone of us here? Matt, having flowers, Travis, and Curtis. Jeremy, how is it going? What time do you work, Jeremy?
I worked from 7 to 11. Managed to talk him into letting me come in later today. Usually it's random, so it's hard to say. Everything's going pretty good with the class so far. Just a lot of remembering, a lot.
About this class, you think? A lot of remembering. But was the homework okay? Like, did you manage?
Nothing too bad. I mean, the last question was like a good review question for me because I haven't seen that stuff in a while. But
Yeah, that was the point. Like last question, I did not give too much hint because that is supposed to be from your background. The first other two questions was expected that we do it here, and mostly that was running the class, so that should help.
yeah, I like this first homework. It made me not feel like I was drowning yet.
Okay, that's good. No, that's a hope. Yeah, but so the point is, that's what I try to tell you. So I know as a student, it's hard to say. Stop me. Tell how that we are getting lost. I'll try to do something. Sometimes it is impossible for me to do much. Like I also have limitations, not because of the curriculum and other things. I don't know how to make it simpler. Like, as simple as that. Like it's my inability to make it simple as a teacher. So, but let's try. Math, how was it?
What was that?
How was the homework?
Homework? I mean, the first two questions we basically did in class, and then the third one, I knew it was all review, and I just kind of ran out of time to do it. So, but I know if I had a little bit more time, I just with working on other things, I could have found time, but I just didn't manage it very well. But I could have done it. Didn't seem too bad.
But you feel comfortable about the question, right? You didn't feel like why
Yeah.
you did this.
Yeah, it wasn't anything too outrageous. It was doable.
That's what did I do? Okay, we have a right here. I posted a new homework. This should connect with whatever you've done in an introductory level course. This is called Ampere's law. That's what we will spend these 2 or 3 lectures on. Earlier, you might have done simpler examples. We will do a little more detailed examples, but different. But the idea is going to be just of Ampere's law, and that's what we'll do for next few. It's so this is homework. Yes. Homework 2. Right. I might be able to finish the topic before that. So, then I'll begin something else. Midterm 1. 2 weeks after that, which is 3 weeks from today. And by now, I think the style of the course should be clear. There are quizzes every lecture, homework about every week, and once in 4 weeks we have the exam. So that's how it's going to be, and then we'll keep repeating. Okay. The problem we discussed earlier was about, we talked about given a magnetic field, what's the force? Right? So given magnetic field, given the magnetic field, find the force. Find force. Force on a charge. And what are we? So what does that mean? So there are two entities here. So there is electric field and magnetic field. Electric field and magnetic field. That's one set of quantities, and the other set of quantities are charge. It's called Q, and there is a current. That's another set of quantities. It's like if you're talking about gravity, there's a mass and there is a gravitational field. Mass creates a gravitational field. Here, there are two ways you can talk about, and what we did here is that given the electric or magnetic field, what is the force it exerts on a charge? Right? That's a problem we can talk about. That means this is given to you. What happens to that? This system, how does it affect that? But we can also talk about given the charges, like for example, how do you create electric and magnetic field? That's created by charge and currents. And you want to do the opposite. And that's what this whole course is about. The first week was the opposite, but that's the simpler scenario. We want to talk about what happens, how are electric and magnetic fields created using charge and current. In general, instead of a point charge, we talk about charge density. So then the notation is rho. So this is a function everywhere in space. That's rho as a function of position. My writing might be bad. This is the Greek letter rho and the position vector r. My r looks like down. And current is current density. You call it J. This is from last semester. When it comes to the first system where electric and magnetic field is given, what happens to the charges? That's given by the Lorentz force. That's what we did. But the opposite is more involved, and that's given by the Maxwell's equation. So let's review Maxwell's equation. So we take this. It's Maxwell's equations. Four of them. So there are four Maxwell's equations. Do you guys remember it? L dot E rho over. So let me write epsilon naught on this side, and let's say, yeah, I'm wondering whether I want to do that on. Yeah, let's write it in terms. Yeah, so let's write epsilon naught E equal to rho. That's charge density. So this is the source of the electric field. And notice, I should also point out here that this is a simplified situation where electric and magnetic field exert a force, or the charges create electric and magnetic field. In more realistic scenarios, this is a coupled form, like always the fields affect this will affect that. And that's hard. We cannot do that in this course. Even at a graduate level, that's hard. So you have to bring in quantum mechanics, or that's what you call it quantum electrodynamics. So that's a relatively advanced topic, and a lot of predictive power there. But J will always talk about one way. Like when we are talking about this way, we say that this is not getting affected, only this. And same thing here, fix this, and what is the effect? We don't talk about the back reaction. It's like saying that when you shoot a bullet, there is a back reaction on your side, right? You get affected. That we are neglecting. We are saying that we are so massive, or whoever is creating this, what are the charges is so massive that is not, or it's negligible, so you can neglect that. So it's like saying if sun was very heavy, when you're talking about the motion of Earth around sun, since sun is so heavy, that is a million times bigger than Earth, you can ask for forget about the motion of sun and just talk about Earth. So that's the kind of approximation going on here. So there is a limitation to that. So that's first Maxwell's equation. Second one. Divergence of B is 0. Divergence of B is 0, okay. Which says that there are no charges for magnetic field. There's no monopole. No north pole and south pole of the magnet can never be separated. Then we have curl. Yeah, curl one. What's the negative change with respect to time of magnetic field? And the same similar thing here, right? So let me write usually, I think the last semester I wrote it as del cross H, but let me write this as del cross B. It should be B over mu naught the way I written here, but I'll move this to the right. Actually, in that spirit, it doesn't matter. So let me write this in rho over epsilon naught. Should not matter, but just bring some similarity in here. Let's charge density over epsilon naught. Here, we have del cross B, the curl of the magnetic field is mu naught J, but that is before that, there is a T so now what is this? Yeah, so that is an E. Something else? E plus mu naught J. What am I missing in this? That's correct. Speed also, there is a mu naught epsilon naught. So this is mu naught epsilon naught. Just to avoid this, I typically don't write it like this. You write next year so that mu naught doesn't show up on this side. But in this case, since we're doing magnetostatics, I like the mu naught. And also remember that 1 over mu naught epsilon naught is C squared. Square root of this is C. That means I can write this as 1 over C squared. Right, so that's one way. Okay, great. So this is still visible. Yeah. So that's your 4 Maxwell's equations. And notice one thing immediately. If you are talking about statics, that means to say time derivative is not there. This goes away. So that's how it gets coupled, right? If you're talking about electric field, magnetic field creates an electric field. Well, change in magnetic field with respect to time creates an electric field. Change in electric field creates magnetic field. That's a coupling. Like these two equations know about magnetic field just because of distance. So if you're doing statics, this goes away. That means magnetic field does not affect electric field, so this gets isolated. These are completely independent points. Like no electric field affected on magnetic field. It will bring it back to these later. And there's one more thing I want to so this is for magnetostatics. Magnetostatics, that's what we want to do. This is of course electrostatics, but these two are electrostatics. There is one more information in here. Let me write that separately. That's not part of Maxwell's equation. Notice there's a contrast here, right? So here the divergence is non-zero, curl is 0. Magnetic field divergence is 0, curl is non-zero. That's why magnetic field is always circular. Curl has to do with circular field. So magnetic field is circular, and electric field is always radial. So that's one thing you want to keep in mind. So there's one confusion that comes in here, which it might bother you, is that current, the way we know, is basically movement of charges. But we are talking about statics, correct? So there could be a small confusion that, oh, what happens to the statics approximation here should we not get rid of this? Because if you get rid of this, then there's nothing, right? That magnetic field will not be there. So we do have current, but then what does it mean to say what kind of currents are allowed? Is any kind of current allowed and time-dependent currents allowed? So what kind of currents are allowed? So let's go back and remember our conservation of charge, which is derived from these four equations. Like if I take a time derivative here and a divergence here and add, so that is a conservation of charge. We did this in the first few weeks of last semester, and also probably the last week of last semester. So that serves as a quiz because we the minor. So derive the equation that I'm going to write. Okay, so the quiz for today is that derive this equation. So conservation of charge says that the time derivative of charge density, this is charge per unit volume, time derivative of that plus the divergence of current density is equal to 0. Okay. And the quiz is to derive. But now I said that we're doing statics. When we're doing statics, all the time dependence is gone. That means the charges are not time dependent. So I get rid of this, which puts a restriction on the kind of currents we talk about. So what does this mean? Divergence. So in magnetostatics, of course, we have these two equations. So that's magnetostatics. But there is an additional requirement that the currents we have, we talk about as sources, should be divergence less. Divergence less means it shouldn't originate from a point. Like there should be no J suddenly appearing out of it. There should be no source of J. Or that it should only come in circles. So a simple way of saying it is that there should always be a current loop. If you're talking about a wire, it should form a loop. Otherwise, you're not doing statics. For example, you can always talk about a finite wire, starts from nowhere and ends nowhere, hypothetically speaking, and there is a current I. But if you were to calculate the divergence of this at this point, there will be a certain source of J. And then here there is a J suddenly disappears. So this will not come off here. So you will always have a loop. Then finish the loop for J. That's the current loop. Current and J. So what the that's another point. We typically talk about current carrying wire, and here we have current density, right? What's the connection between the two? So what's the connection between current density and current in your introductory topics? How do you define J? Let's say magnitude. Because in introductory physics, even introduce the vector nature. So, what is current? Like charge density is charge per unit volume, right? Current density is yes, if it is yeah, that's correct. UV over volume, correct? So what's the connection with I, the current? Yes, so that's current per unit area. So this is current per unit area. Area of what? Area of a current carrying wire. So this is a wire. That's the area. So that's I. Simple. And that's your area A. Cross-sectional area of that's what we're talking about. But I want to write this in terms of of vectors, and the idea is I is equal to vector j dotted with area is a vector, remember, let's be A. But sometimes we also say current density, right? It's also volume. So what you say is that put a dl, dl, you multiply in here, and you multiply dl. Remember, current has a direction, right? So this is the small element there, and then you can see that this is a volume. So then you can say I times dl, current times the line element divided by the volume is also current density. In that sense, it's a current density. That's why you say current density, because it also can be thought of as a volume. There. But this is what we will try to use or be useful. We'll see as we go, we will get that clear in examples. So the main equation we have is the divergence of P is 0 and divergence of curl of P is equal to J. So of course we have divergence of D is equal to 0. It's always true, irrespective of whether it was static or not. And we have another equation, which is what we want to concentrate on now. Your L cross B is equal to mu naught J. So J acts like a source of the magnetic field. And now, whenever we have a curl, think of your Gauss's law. So similarly, we want to derive an Ampere's law to be a consequence of this equation. This equation is true at every point in space. So this is a point, any point in space. This is also any point in space. At every point, this equation is valid. Imagine a surface of your choice. This is not a physical surface. When we were doing Gauss's law, if you remember, there were two kinds of surface. One is that actually there is a surface charge. So, and there's another where you think of an abstract surface where electric field is going through. So similarly, this is an abstract surface. You could pick any surface of the class and think of a magnetic field going through this. So, like this. That could be your magnetic field line. That's your surface, some imaginary surface. That's not a real surface. I want to emphasize that's an imaginary surface. I'm just thinking of it like that, and that's your S. So on that surface, I integrate. So I calculate this equation on left and right hand side at each point on the surface. Each one is a vector, and then I add it up in the sense I first take a dot product. So at each point, I calculate dA. dA will be perpendicular to that. That's dA. It doesn't have to be tangent to this. This could be surface, could be in any direction related to the magnetic field. So I take the dot product in each point of this equation. That's perfectly fine. And this is J dA dotted with J. Already you see what I've defined earlier. The right hand side is nothing but current. But to do that, I integrate. Where do I integrate? At every point on the surface, and I add it. That's what integration is. I do this, and I add up. And I learned that on the right hand side, that's nothing but the current, but the definition of current going through the charge. I haven't shown you, so this is our magnetic field I have shown you, but that could be currents that are creating this magnetic field. Magnetic field is created by the currents, and I've not shown you here, but that could be, let's say, that would be a wire going through. This is like current carrying wire. But there must be more current carrying wires because this is a complicated thing that the magnetic field created by the I, and remember, magnetic fields are circular with respect to the current carrying wire. So this, if this is creating this, that means there will be a complicated structure of height. And it could also be that wire is going in and it is going through again here, coming out. It could be a complicated arrangement. Right? So some complicated current carrying wires are creating this magnetic field, but take an arbitrary surface and ask how many currents are going through the charge. So this is mu naught times current enclosed. Now that brings in a definition here. What do I mean by current enclosed? Calculate all the currents, and there is a direction also here. Certain currents are coming out of the surface, certain currents are going into the surface. So there is a notation in here. Is it positive or negative? And I'll come to that notation in a minute. There will be a right-handedness in here. But before that, let's go to the left-hand side. What is the left-hand side equal to? There is a theorem in calculus, vector calculus. No.
Superimpose the integral it's Gauss's theorem.
Yeah, but that's so what you're thinking about is this one. So that's jotted with, let's say, some m is equal. So this is the volume element, right? And this is equal to a surface. Right? That's your part. That's divergence here. Right? What it means is that if you're integrating a divergence of a quantity on a volume, it's only on the surface it contributes. Instead of doing the divergence on the volume, do it only on the surface, but forget the derivative. Right? And this is we should always think of it like this. In calculus, that is this. If you have the x, this is visible. The x, d by x of a function, what is this equal to? B minus f of a. This sounds very simple, but notice what it is saying. If there is a derivative of a function, integral negates the derivative and it contributes only on the boundary. It doesn't care what the function is in between. It's only the boundary points that contributes. It's the same idea here, but now this is the volume. There is a derivative of something. It's a more complicated expression because it is the divergence. But whatever it is, it's a derivative. So it can survive only on the boundary. And the boundary of a volume is a surface. Right? And if it is a divergence, it has this nice feature that instead of forget this derivative, so there is if you think of it dimensionally, derivative is 1 over length. One of the lengths cancel one of the volume elements length. So you have left out of the area and area dotted with m. Right? So that's divergence theorem, and that's for a volume. Surface of a volume, boundary of a volume is a surface. Here we are doing something different. This is called divergence theorem or Gauss's law or Green's theorem. There is a corresponding one more theorem you learn in your vector calculus, which talks about a surface. It's clear now that what's the boundary of a surface? Curve, like a line, like it's a closed curve. So this is going to survive only on a line. So you call it a line integral, right? And instead of and this becomes b dot into dl. This is called the Stokes theorem. Familiar? You must have seen it in some form or the other. Now, what is the geometry of this? So, how you motivate this is you should look up your vector calculus to see the detailed proof, but that's not very. It's not very insightful. The main idea is here. So this is your surface, let's say, and I'm putting it on a plane purposefully. And curl of a vector field is basically all these tiny elements. Right? If I'm doing a surface, I break this surface into small pieces. Like instead of calculating this on this complete surface, I say that surface is nothing but broken into many pieces, and each one of them can be thought of as a loop. Like because this is the loop integral. And the same thing, I'll tell you what the sense of the direction. Is that visible online? Right. And notice one of the loops goes this way and the top loop goes the opposite way. So this is that way, or the other loop here will go the opposite way. So all the inside lines will cancel out when you're adding up. When you add up all the surface elements for each of the loops, they all balance out, and it is only on the boundary that they survive. Is that clear? My point that I'm making? Like what I'm saying is that there are two big, suppose I make this here only on one, all right? So I have this going this way, and the second loop goes this way, and notice these balance out, right? I have ones go that way, ones go the opposite way, they cancel out, so and will drop it. Right? There is no contribution from that. Go to the next one, keep doing that. All the inside ones cancel out, but outside ones don't cancel out. So that they are the only ones that survive. So in that sense, this is lots of loops contributing, but it's only the boundary that contributes. So it's much easier, instead of calculating something on the whole surface, you calculate it only on the line. So very similar, but entirely different. So these are the three quantities, right? Volume integral contributes only on the surface, which is the boundary of the volume. Surface integral contributes only on a line, which is a closed line, which is the boundary of a surface. And here, this is actually getting integrated on a line, right? This is a one-dimensional case. And the boundary of a line is 2 points. And that's your 2 points. Right? That's the three quantities you can think of. And this is Gauss's law, which we have done before. This is a loop integral. Like Gauss's law involves surface integral, and now we're talking about loop integral. And that's Ampere's law, if you want, right? So that's Ampere's law. So how do we use this? This is an example. All right. Wait. Okay. So example. Yeah. Let's do the simple, quick example. I'll come back and do this again with more stringent assumptions that we are making. So again, if del cross B is J, Ampere's law should be true, right? That's the understanding. And a very generic if statics So let's take the simplest example of having just one wire. Right? So we just have one wire, and it's coming out of the board. Right? So that dot means that it is coming out of the board. So this becomes so this is a current carrying one. So this is wire coming out of the board, out of the board. I want to create a magnetic field. By the way, what is the magnetic field associated with the current carrying wire? What kind of magnetic field will be there around a wire? Uniform
Yes, magnitude.
magnitude or anything. Just tell me what it is. What will it look like?
Oh, sure.
It will be circular, right? So it will be circular around this, and it will get weaker as you get power and power. So it's not constant like for solenoid, it's constant. But for a simple wire, it will be very large and get closer and it gets power and power. That brings me to the point here that I said there's a notation inbuilt in here. When I say enclosed, which one do I choose positive and which one do I choose negative, right? So there's a ambiguity in here. How do I get the sign here? Notice that whenever there is a loop here, so in this loop, first I decide the surface. That's your surface, and I have to choose which side am I talking about. So dA, right? So dA has a direction. The area of the surface, I will choose this coming out of the board or going into the board. If it is having a shape, it's always the outside that is taken for positive. But flat case, there is an ambiguity, right? Which side is the inside or outside. Pick one. So, for example, I say that this is coming out of the board. The moment you say this is coming out of the board, there is a right-handedness that comes in. And right-handedness means that if the area is coming out, the counterclockwise is where this loop goes. So this loop could go counterclockwise or clockwise. So with respect to the area vector, this goes counterclockwise. Right? That's the right-handedness nature of that. And with respect to that, the current coming out of the loop is positive. Right? So anything in the direction of A is positive current. Going into is negative. So there is a right-handedness inbuilt in Stokes' theorem. That's important. Okay? So, but again, in the problems that we do, it won't play a signal, it won't be too error-prone, but it is good to remember that there is an assumption involved. Okay, so that's your current carrying wire. And I need to pick a surface now, and I need to pick the surface of the circle. Surface. Remember, that's an abstract surface. Right? There is nothing at that point. There is nothing sitting, and there is just an abstract surface. And the radius, I say, is rho. Instead of r, I choose rho. I don't think it usually is a confusion with the charge density. This is the cylindrical coordinate rho. Cylindrical coordinate rho, and there will be an angle also. If you have an axial quantity and we're saying this is infinitely long wire, whether you are at this point or this point, there should be no angular dependence in it. If there is one wire, long, infinitely long wire with no feature on it, which direction you look from it, everything will look the same. If you just have one wire, all directions will look the same. So we can conclude by symmetry that magnetic field cannot depend on the angle. Right? So that's a symmetry argument. Magnetic field cannot depend on an angle, and it cannot also depend on z. Whether you're here or here, it could be the same because it's infinitely long. Like if I move a little bit up or down, it should not matter. So symmetry requirements, symmetry requirement is that B is equal to having only rho dependency. It has no angle dependence, it has no Z dependence. Make that more explicit. That could be an angle dependent, that could be Z dependent. I strike that out. No angle dependence, no Z dependent. That's because it's an infinitely long wire. Its result works only for that. What's the direction of that? What is that? It has to be, the magnetic field cannot have any divergence. The divergence has to be 0. That makes me choose that this has to be in the direction of curl. Like it can have only a curl. Magnetic field cannot have a divergence, so that makes it having a curl. All this is an assumption. It's motivated from symmetry, assuming that this is infinitely long. It cannot have any structure. I'm not using Ampere's law. The symmetry argument usually is harder in an unknown situation. As we know, you have used this so much that there are ways you can check this. But if you're in an unknown territory, sometimes looking for symmetry could be very hard in a new situation. So that's our assumption. And now we use our Ampere's law for this surface. What is the right hand side? Right hand side is clear. That is only one current, right? That's just I. So there is only one current coming out of this the surface, and that's I. And the left hand side is a loop integral now. I will go clockwise because I said I is coming out. So there's a dl here. That's my dl. That's the dl. What's the direction of dl? It's in the direction of tangent to that. That's direction phi. Right. So my Ampere's law tells me this is dl. It is dl times phi. And the magnetic field is already in the phi hat direction. So I say this is phi hat times d. That's the magnitude of rho. Phi hat is 1. That goes away. And all over the circle, the rho is a constant. Right? I am choosing this to be a circle. Everywhere on the circle, rho is a constant. So I can just bring that out of that integral because everywhere it's the same. So this is b rho comes out of it. What is remaining is the line integral dl for a circle, which is the magnitude of that, no more vector, which will just be the circumference of the circle. So q pi times rho. So q pi times rho is equal to mu naught times I. And that immediately gives the magnetic field for a current carrying wire. The magnitude of that direction is circular, we already said. E of rho, we know, is equal to mu naught I over 2 pi rho. Since because of our units, it's often, at least I try to write this in this form, because if you're using another textbook where they are not using SI units, instead they are using Gaussian units, then they will just omit this mu naught over 4 pi. Then you have to multiply by 2 pi over rho. True that 2 can be cancelled out, but in your Griffiths textbook that we are using, that writes this mu naught over 4 pi. That, but you will see many textbooks. It's very common to find they will just omit this whole thing. That's because they're using another units. So it depends on the current, and it's inversely proportional to the radial distance. It is not the spherical coordinate, it's a cylindrical coordinate, perpendicular line to the current. Right? So Ampere's law immediately use this. And next time we'll come and do other examples, especially solenoid. gives you nice, neat results. And we'll do this. And you have a lot of, and we'll actually also do what if this was a bit. For example, yeah, this is a good question to ask. If you have a current carrying wire, like you have the power lines, does that current go in the inside part of the wire or on the outside part of the wire, or is it everywhere? Inside. Any other answers?
You're talking about like the high tension power line?
Yeah, take any wire, let's say. Take your favorite wire. And ask, is it uniformly, the current, is it uniformly going to the wire, or is it inside, or is it outside?
So we just run through the copper on the inside. That's how we the insulation. The wire.
Forget the insulation part, that's just the copper. Okay. So copper has a volume, right? Let's say 2 millimeter wire. And if you are talking about a high tension, that just take. So let's take some length L. More current go in the center, or more current goes on the surface?
That's on the surface because the less going into less obstacles to collide with, for instance.
Just because of the conductor. Remember, on a conductor, all the charges want to stay on the surface, right? And electric field doesn't like to be inside the surface. So most of the current actually is on the surface. In fact, that becomes a big deal because if you have a high tension wire, that's an expensive material there. So why spend so much money on building the inside part? So make it empty. And they do that, I think. Or maybe that's why they have this twisting going on. I'm not sure. I'm going into. I really don't know why they twist it. It might be because of the strength also. But I do know that they play tricks with saving because money is important. Economical. So you do things there on the surface. So we will talk about those things more. If there is a current distribution in the inside also, like if it's not a metal, then it's only for a conductor that it goes on the outside. If it is any other material, if it is not a perfect conductor, then there is a good amount that can go. But most of the time, we have metals and it's mostly on the surface. So if you're sitting inside of the wire, you won't get shocked. But anyway, you won't get shocked. That's something else. Yeah, so that's a good information. Look it up. Like all this played a very important role when the first time they were having cross-Atlantic cables for telephones. Like this was in before light came, like before Maxwell's equation, like in the 1860s. Like that was a big deal about having telephone wires being laid out in the Atlantic, all the way from Europe to, I think it was in Canada. Is that right there? So they were trying that, and so they used to keep boosters. So basically, they don't go very deep, about maybe 50 meters or so. It was a big project, and this came out to be an important factor. So how much dissipation is there? So how often do you put a booster? Like because it will decay, right? The signal will decay and you want to boost it again. And how often do you want to do this? There was one of the engineers proposed that this is the way to go, but that was not the right way. So this became a very big media and there was a huge controversy. And it did collapse the whole thing. That the Lorentz equation, Kelvin, the guy whose name as Kelvin, his name is actually Thompson. He took it over with a very public event. So he took it over, and then that was completed in the next part of the year. But then very soon, within 30 years, they got this light going on. Light becomes constant. I suppose that exactly. But that's a very controversial history. So, and you look back at that time, so sure that's not the most pleasant thing. Okay, I'll stop here. I already crossed. Oh, not that. But still, I couldn't. So, it's easier for you guys. You just have to click that button now, right? If you're online to get from one class to the other. some stuff online.
Yeah, it's not too bad.
Okay, enjoy, guys. Have a good weekend.
Go back to Neckers or
Yeah, let's meet in next. That would be good, right? I'll see you there. Okay. Take this off.